the organizers assigned to me this topic, from cosmic rays to Kobe and beyond, and of course this links a lot to my experiences with Louis and the help I got from Louis in getting things along. The talk I wanted to give was this one, which shows that Bob is a little behind because I also spent some time in Russia now, but I want to say I dug out this old. Unfortunately, I was traveling when I was making a talk. I dug out this old magazine article by Viola, which commemorated Louis after his death, and it talked about the fruitful inventive mind. And when I was first thinking back about Louis, I was thinking about how creative and inventive he was, and about how much more, and about setting standards and so forth. And I thought about the kind of stuff and the advice I got from Louis. And you all know you got told advice from Louis many times, but in fact, the most effective thing he did was teach by example. But he did always try and teach us to think. You know, first think broadly about what was going on, and then think deeply about the thing that you need to do. And also, more importantly, to think big. And so we had the example from Art and Jack Lloyd and so forth, that they were big headaches. You know, he thought up things, and you saw I took 2 or 3 pieces of technology that were coming together and put them together to enable some new project. And that was one of the things he was always telling us, that when you finish an exciting experiment, that is when you've got to a point where you've taken data and you've analyzed the data, and you're thinking about what you might do next, your natural instinct is think how to make that same experiment better and do it again, right? How to improve on that. He said, stop at that point. Yes, keep those ideas, but think about what else is new, what new developments there have been, what new technologies and new tools there are, and see what new ideas and things can be brought to bear on a whole new experiment or a whole new thing that might be very important and generate a whole new way to do it. And then he said, make sure you calculate it so that you ensure you know what you're doing, that it's actually going to work, right? And sometimes I think he calculated it pretty far, but he left it up to some of us to solve some of the more serious problems. But I think the thing that was the most effective to me was the fact that Louis did these things, and I saw him do it, or I was there in the aftermath and saw what happened as a result of that. And that just told me, how do you do that? And that's why I think LBL was so effective. There were a whole set of people who were actually thinking on this kind of scale and doing things on a scale that most other people were afraid to try and start to do. And that was, and I'll come back to this sort of at the end, even though I'll run out of time, and say, you know, it's a combination. I don't know whether it was Louis teaching me this or that was my natural inclination, and that's why I stayed, because it was a place where it was encouraged, but it resonated with me very strongly. Okay, so let me do the task that was set out before. So this is the cosmic rays. As you know, I came a little late compared to some of the people you've heard from. When I arrived at Berkeley, it was Group A, and I was hired into what was Louis' alternate group, which was the cosmic, you know, the beginning of doing stuff that was considered not high-energy physics at the time, the cosmic rays. And so here's a picture of a balloon backlit by the sun. We were preparing for launch in Texas of one of the things. So I figured a pretty picture is worth a lot more than some words. And here's the idea that Louis had. So it's in the upper right. And I assume there's a pointer here somewhere. There's in the upper right. It's the idea that he had been using in his experiments at the accelerators, you know, at the 88-inch and then at the Bevatron and so forth, was basically magnetic spectrometers to bend the particles and get their momentum. It also tells you the direction that bends, if you know the direction they're going, tells you the sign of the particle. He knew that, understood it very well, and he realized this was a great tool for analyzing the cosmic rays and learning about their properties. And he said he had the great idea that you should be able to put a superconducting magnet into near space, which in this case was a balloon, right? And so, okay, engineers, go ahead and do this. Right? Now, you have to understand that back in the 1960s, when this idea first came up, superconducting magnets were not that common. It's actually a big step to go from simple superconducting magnets in the lab to superconducting magnets that are light enough to put in a balloon along with the cryogens and get them up into high altitude and have cosmic rays. But Louis envisioned this. He knew it was the right tool. And what we see, in what I'll show you in a sequence of a couple slides, but to take words, he revolutionized cosmic rays to where, at the time, this was the only group that was starting to do things with magnetic spectrometers, and except for a few people who flew in a magnet with an emulsion, but even that didn't work very well. But to do superconducting magnets and make magnetic spectrometers moved people away from using calorimeters and other things to where most of the people ended up using magnetic spectrometers. And so here's a picture of the second generation of the things where you can see it. Well, it's cut off, unfortunately, in the picture. There's a stack, which is the vent stack for the cryogens. And there's a superconducting magnet on one end and a camera on the other end. That's because we didn't have, digital readout position measuring devices in those days. We took pictures in spark chambers and then used the bubble chamber kind of techniques to measure the positions and find out what's going on and so forth. And this is our invention of a chrome crush pads that were made of styrofoam and so forth. And this is Doug Heine, who some of you remember, and Hal Doherty and Charles Orth, some of you may remember. And the particular thing that Louis was most interested in here, besides the original idea of studying high-energy physics interactions, and here Louis made one of his mistakes, which is he saw too far in the future that there was going to be a day when people weren't going to build a next generation accelerator and you were going to have to get at high-energy physics some other way. And he was right, but he was more than 20 years ahead of his time. Right? We see that. But he started this program, he started the HAPPY program, and then that devolved into doing cosmic ray and universe science. And the thing that he was most interested in was the question about antimatter. And so what he knew very well, and everybody in particle physics knew, is that every time you converted some matter, some energy into matter, it was an equal amount of antimatter. There had to be a balance in that situation. And so the question was, if we go back to the early universe when it was very hot and there was an exchange of matter and energy going on back and forth, we knew there's roughly equal amounts of matter and antimatter. Where is all that antimatter today? And that was a problem he wanted us to address. And he thought the magnetic spectrometer was the right way to do it. You let the particles come in from the top, measure a time of flight so you know direction it's going, measure if it bends this way or bends the other way, and that would allow us to be searching for antimatter. And then Louis just gave us the job and said, go to it, right? And he came back when we had the data and asked, do we have any good antimatter candidates, right? And there's a long story about event 26262, but we won't go into that right now. But Louis, again, that was an example of Louis picking out the important question, picking out the right techniques to go after that, and then when we actually started to have candidates, things that are real, go in and look at them very carefully and make sure that they were correct, that somebody else couldn't knock it down. We had other examples of that. And so here are pictures of, this is supposed to represent a cosmic ray coming in the atmosphere. The reason you have to go high in the atmosphere. Here's another balloon going up. But it wasn't so long till people were building magnetic spectrometers and flying from Antarctica, flying from other places just to get long exposures. But we knew that eventually you had to go into space. And so we had a HEO thing that was unfortunately canceled because the Mars landers ran over budget. Then we restarted with a big project which was called Astromag on Space Station. And this is a picture of the T-shirt. That I still have a lot of those T-shirts if anybody wants to buy one. But we were all set to build a superconducting magnet on this, magnetic spectrometer on the space station. It's picked out here on a nice little arm so it wouldn't magnetically affect the rest of the space station. You'll see that it's actually been realized now, as Moish mentioned, I believe. But the concept was, there are multi-wavelengths. It was part of NASA's overall program, measuring X-rays and gamma rays and optical things and cosmic rays to try and understand what's the dynamic balance of the galaxy and extragalactic kinds of things. So we had even a nice outreach brochure in those days. And the thing that I find interesting is eventually this thing was actually realized, the Sam Ting's collaboration, the head of it, after you guys kicked him out of L-Star. then you know, he found the new projects to do. But the interesting thing is, this is their logo, which is back-to-back universes, the matter universe and the antimatter universe, which is the wrong thing. But in principle, AMS is on the space station for 20 years, and it's going to search for the existence of antimatter to the edge of the universe. Well, that's a little extreme, at least to the next galaxy cluster, right? So here's an actual picture of AMS, which has a superconducting magnet that was, at first it was a permanent magnet, rare earth permanent magnet, then a superconducting magnet, and then there were leaks and things had to be fixed, and back to various things. But this is the scale and the size of it, and it actually exists on the space station. Here's a picture of it in place on the space station. And it doesn't stand up quite as far as Astromag was going to, but it has less of a fringe field because of its particular design. But so Louis's vision that started, you know, back at the end of the 60s of putting a superconducting magnet on balloons and then into space, eventually is realized, but eventually it revolutionized the field all steps along the way. There were a whole series of balloon experiments, and there were a whole series of things that were meant to be space experiments that led up to that. And it's also led to one of my few patents, which I share with Bill Pope, who's here somewhere, and for something to keep, you know, phase separation of superfluid helium from happening badly. And we actually had antimatter limits that made a lot of sense. So we mentioned the anti-Buffington before. Here's the limits on anti-helium to helium as a function of energy, and now the first AMS results. And now these results are going to be migrating down now that AMS is up and working. And here are our results way back from 1975, right? At the 10 to the, you know, sorry, here D, at the 10 to the minus 4 level. And then AMS finally beat that in 98. And now these limits are going down steadily, should improve by 2 orders of magnitude. But this is the point where I started taking Louis's advice seriously. When we got down to the matter-antimatter limit at 10 to the minus 4, that meant none of the neighboring stars were made of antimatter. And one of the things that my cell phone is bothering me? Sorry. I'll turn it off. Okay. So you know, one of the things that Louis and his friend Hannes Alfvén, who also was a Nobel laureate, were fond of saying, you can tell by looking whether a star is an anti-star or, you know, a regular matter star. But by going to 10 to the minus 4, that meant we were searching a region which is many thousands of stars in extent, you know, and we were seeing that there was no antimatter at the 10 to the minus 4 level in that kind of region, which to me meant that antimatter was separated at least on galactic scale, and then we were beginning to have measurements from gamma ray telescopes on balloons. They were saying that even in clusters of galaxies, you weren't seeing annihilation, so it's separated on a larger scale. And I'm saying, all right, there's no antimatter present, so it's got to be coming, you know, that effect has to come from somewhere else. And I said, it's time for me to think about doing other experiments. And so this is the time Rich remembers when we were exploring things like a xenon Compton telescope, many other kinds of things. And you know, this is the time when I started to make the transition to the cosmic microwave background. But I'll come back to that in a second, because something I was doing earlier this week is the 300th anniversary of Mikhail Lomosov, who you guys probably don't know, but he's a very famous person in Russia because he actually created the first university in Russia, which is Moscow State University, and he was born in the far north and apparently walked 2,000 kilometers to Moscow to get a high school education, and then he went to Germany to get a university education and realized how great universities were and came back and convinced the Tsar that he should build a university in Russia and so forth. So they're celebrating his 300th anniversary, but he was also a great scientist and pretty much like Louis, a polymath. He covered many areas, and one of the things, he did a lot of geology, he did a lot of chemistry, a lot of things like that. But one of the things he invented was a telescope, and for its 300th anniversary, we're making a special satellite which has a telescope on it. So here's the telescope. This is Russian for gamma ray burst, I think. My Russian isn't quite that good. But the idea is there are gamma ray bursts, roughly one a day. And so we've built a burst detector that can detect these bursts and get roughly the pointing. And then we have an optical telescope that can slew around and look at the light, the ultraviolet light, and then the optical light from this in a very short time period. And this satellite was supposed to launch on Tuesday, but because of various issues, it's not going to launch until sometime in the spring. But we still had to have the celebration of Lomonosov's 300th anniversary, just like we're having the celebration of Louis' anniversary. Okay, so back to the cosmic background, the transition from me working in cosmic rays with Louis, and which was the thing that the reason I knew it as Group A, and you guys knew it as the Alvarez group, although occasionally people would say Alvarez group, was Louis, in some of his discussions with the DOE, was told he couldn't spend some of his money for some of these projects, and so he changed the name of the group, or whatever it is. But anyway, for those who were here, they kind of know the story even better than I. By the time I arrived, it was Group A, and Louis was liking to tweak the administration, and so I was brought into an environment where that was considered okay. And so we started with a set of experiments, and so the first was this U2 experiment where we built differential microwave radiometers to look at different parts of the sky, and then we followed that with a balloon experiment, and then eventually with the Cosmic Background Explorer satellite, COBE. And the one key issue, so Louis helped us get started on these projects, not so much in the balloon, but he helped us get started with the U2 experiment. That is, we actually were proposing, I think, to do it on the Learjet, and he convinced his friend Hans Mark, who was head of NASA Ames, to let us think about doing it on the U2, which was a more aggressive kind of thing to do, and allowed us to go forward on that. And then I went on and did the balloon stuff sort of on my own, because we've been doing balloons before. We knew that system. But when it came time to respond to NASA's announcement of opportunity number 6 and 7, and you think of NASA having been flying satellites for a long time, but this was only the 6th and the 7th time they'd asked for proposals from the rest of the world, that we put in a proposal in July of 1974, which I sort of drafted together, but Louis was the PI, which gave it a lot of credibility, and I was a co-I, and Louis not only did that and encouraged it, but when it was time to make the presentations for the face-offs of the different proposals, Louis came to Washington and sat in the audience, right, and supported it. And that's something that he was doing, which was he was taking his young guys and giving them opportunities and encouraging them along. He would help us get seed money, and then he would help us try and get started, and then we'd have to survive on our own. And so as a result of that, we got a little bit of study money, which we did a study, and then in March of 1976, which is an extremely long time ago, NASA headquarters established a science study group that had 6 people in it, and then the three people who were the PIs were there, and we were all quite young then. John Mather was also from Berkeley at the time, and Mike Hauser was slightly older, but we were all quite young in those days, and we're not quite so young anymore. But the result of that was that 2 of us got Nobel Prizes in 2006. Okay, whoops. So now I'm going to talk to you about what is it we're trying to do in cosmology, what we're trying to understand. And our primary tool is that we're trying to reconstruct what happened over the entire history of the universe and what might happen in the future. And our primary tool is that the universe is so big that it's a light delay line, right? So that you can, if you're on the Earth and you look out to different distances, you can see back to different epochs in time. And you know, if you're looking at the nearby stars, you're only looking back 10 years, but if you're looking at a typical star in the galaxy, it's thousands of years, to hundreds of thousands of a year, to 100,000 years. But if you look at Andromeda, you're looking back and seeing Andromeda the way it was 2 million years ago, a typical galaxy 1 billion years ago. And if you look back as far as you can to when the universe was 1,000 times smaller, you're looking back to a time when the universe was roughly 300,000 years old out of its 13 billion years. So if you can make a series of measurements of concentric spheres around us, you can make a series of measurements of samples of the universe as a function of its history. So that if you can map the universe, physically map the universe back to this beginning of time, you can actually map its history during the same way. And so the concept that we have is fairly simple. We live in a spiral galaxy. We live in a spiral arm of a spiral galaxy about there in the center. We look around, we see our galaxy. We look around us further distance out. We see what look like present-day galaxies, beautiful spiral galaxies, elliptical galaxies. But they're pretty well formed and pretty well developed. If we go out a little further, we're going to see, well, cut-off galaxies. So we look out a little further, we're seeing galaxies as they're first forming, and they're irregular shape. Many of them are smaller, but they have a very different behavior. Now, the only problem with this in the real universe is this only shows a few galaxies. There should be about 100 billion of them inside of our universe. And then if you look out very far, you see the cosmic microwave background, which now we know has this beautiful pattern in it. And then if you could see a little bit further, you would see the beginning of time. So that's the basic idea behind what we're trying to do. And a tremendous amount of effort and money now has been spent in trying to make the maps relatively nearby, and especially these maps at the very beginning of the universe, which we have to extremely high precision. Okay, and so in fact, you can see how much money has been spent. We have the COBE satellite, which made the original discovery. We showed it was a relic radiation from the Big Bang and made the discoveries originally anisotropies. The WMAP satellite, which finished 7 years of observation, has been shut down and has made a much higher angular resolution map. And now the Planck satellite, which is currently operating, is making even a higher resolution map, currently making a higher resolution map, and at more wavelengths, so we can do it. And this smudgy part means we're also measuring the polarization, which is providing some additional information. So here's a picture of what goes on. Here's the third version of the satellite. So we're refining it. So if you thought about Louis coming to you and say, what you've got to do is take something that's cooled to 1/10 of a Kelvin and put it out in the deep space and spin it around and send the data back to the ground, you would have said that's a problem thing to do, but that's the kind of thing that we eventually evolved to. And so here's the satellite. Here's the data coming in. We're not painting the sky. The sky's painting the detector, right? So this is actual data from the first year. This is the plane of our galaxy. Right? And so the white is mostly stuff from our own galaxy. The red out here are the fluctuations of the microwave background, but there are 9 wavelengths being overlaid here. So you get dominated by the structure on the galaxy. And then we take these maps and we split them open and we rotate around so that we're in galactic coordinates. Right? So you see the galaxy dominates, but out here is where we begin to see the original universe. This is what an optical map of the sky looks like. You see Magellanic clouds and you see our galaxy, and that's about it. And so that's where we are, and that's come up to give us this idea of the history of the universe, starting from the present. So we can see a sphere around us that's 13.7 billion light years in radius approximately, that has modern galaxies in it. If we trace this sphere backwards, we find the radius of that sphere has actually been increasing at an increasing rate. That's why it's concave out. But earlier it was decreasing and going down until you get back to when the universe was 1,000 times smaller, and then it was the temperature of the sun. That's what we're measuring here. There's a dark ages in between and the first stars, sort of the dawn of the universe and the storm. But even earlier, we're extrapolating back, and we think we have another accelerating phase, so that everything that's in the 13.7 billion years in every light years in every direction was once in a region smaller than an atom, right, down to particle physics size, where quantum mechanics is important. And so we have this whole picture, and we can calculate it, and then we're going to compare it with these concentric spheres of observations to see what we've learned. Now, to make sure I get to them, I want to show the movies. So it means I have to have the lights down. I want to show you a couple of movies, one from 1997. Okay, so this is a movie that you might well know. This is a movie about a researcher who's looking for signals from extraterrestrial life and receives a signal and its instructions on how to build a machine that would let her travel to visit these aliens. And she has to travel across the universe and visit the aliens. And so she gets to go by all the stuff that we knew at the time. So we knew about the Earth. This is 1997, so it's long ago. We knew about the moon. And as you can guess, we know about Mars. And maybe Phoebus, if it's in there. And the asteroids, well, these are not real pictures of the asteroids. Some of those pictures were actual pictures of the planet. And we knew about Jupiter. And it wasn't that long before that there was direct evidence that the giant red spot on Jupiter was a big hurricane. And so that's in the movie. And we know what's beyond Jupiter, right? Saturn. You guys are supposed to know that. There will be a quiz, right? And then we'll skip some of the other planets. But it's very nice these planets lined up, right? But if you remember, 1997 wasn't so long after the Grand Tour, so they were kind of lined up. And this is the Kuiper belt, and then the Oort cloud, which is the primordial leftover material from the formation of the solar system. And then we're going to get to see other stars. This doesn't take that long, but it's pretty pictures. And this is one of the early pictures from Hubble. Hubble's been up for a while. This is called the Pillars of Creation. It's a giant gas, dust, and molecular cloud. And when the stars are formed, they blow the dust away into these segregated columns and so forth, so that you can actually see into the stars. And then they superimpose it on a nebula, so that it looks quite beautiful. And it's nice that they all line up for this trip. And then you see that we live in a, kind of yellow, purplish galaxy, which is kind of lovely to be in. And Andromeda's not so far away, and Andromeda has some satellites. And for some reason, they put one more galaxy in, which isn't quite right, but we get to go right through a galaxy. And you notice there's a lot of galaxies out there. Remember I told you there's on the scale of 100 billion. And we pick up a little speed. The mean travel time between galaxies is 2 billion years, so. And you end up in a room where you get to talk to the aliens. So that's a cool trip. Okay, well, that's what we knew in 1997. Now I'm going to show you a movie we made last summer. And it starts from the highest point on the Earth, and it's based on, everything is based on real data. Now I have some inspiring music, too. So from the lowest point on the Earth to the highest point on the Earth is about 28 kilometers. The Earth's radius is 6,400 kilometers. So that's apart in 2,000, essentially. So the Earth is actually a sphere, even though right now you're just seeing all the textures, right? You're seeing all the structures on the Earth. But when we get further away, you'll notice how perfect a sphere the Earth is. Right? All these features that show up so strong to us in everyday life is not very important on the actual Earth itself. But we've made some more advances since 1997. We've put up a lot of artificial satellites, a lot more. And you can see the various orbits, including some long elliptical orbits, which the Molina orbits, the Russians like to do, but also a particular band that is in white here, which is a geosynchronous orbit, which is essentially full of our communication satellites. There's every degree, which is about the spacing you can have, there's a satellite. It's pretty much all used up. Okay, so we're out to a light second. That means we've reached as far as the moon. So now we're not going to fly by all the planets because you saw those pictures before. And besides, on the scale of the universe, the planets are not very important. So now you'll see the constellations. And you'll note they'll distort as we get further away. And that's as far as radio signals from humans have gotten. Slightly distorted because of the projector. And again, we have to go to sort of a painted, of impressionist painting of the galaxy. Now, these are real galaxies. Every one of these is a known galaxy. So we've mapped over 1 million galaxies. So this is beginning to sound like bubble chamber pictures. And then you can't see all the galaxies because our telescope's not big enough yet. But you can see the large red luminous galaxies and the quasars further away. And then you can see the cosmic microwave background. And we passed right through that, right through past the beginning of time. So we have to go back. It's just so you can, have time to decompress. So we have to do the same sort of thing the scanning does. We have to keep on a Moore's law of mapping galaxies. First 1 million. Now we're trying to do 1 million a year, and then later on we want to be doing, 5 million a year. But that's part of the effort and so forth that we need if we're going to actually measure a lot. And you have to figure out how long that takes you before you can get to 100 billion, right? It takes a while. When you get to 50 million, you've begun to dent things, right? So this is like powers of 10 without all the numbers. So the Earth is very round, but when you get close, you're just mostly notice the features. But what you have to understand is that Earth is 20 times rougher than the universe. Okay, thank you, Bob. I want him to show the end of the picture, so I'll leave room for the, I'll skip over whatever slides I have to. So when you get close, you actually start seeing a lot of large-scale structure to the small surface features on the Earth. Okay, is everybody decompressed? Now if I can get back to this. Okay, so we have this theoretical model. Unfortunately, it says there's at least 4 pieces of new physics beyond the standard model which we need in order to even explain the world we have today, and hints that there may be other things, or at least other things we should check for. But we can calculate them and we can see whether they compare to those kinds of observations that we're making. So let me explain to you about how those galaxy maps were made. So here is the Sloan Digital Sky Survey, which has 1 million galaxies in it. And it's made by simply taking pictures of the sky, throwing away the stars, selecting the things that you believe are galaxies, getting their 2 angles on the sky, and then estimating their distance and plotting that up. As the Earth rotates, you take a series of pictures, you get a fan across the sky. So you see the kind of fan that we have here. And then here's a movie that shows you the actual survey, and every little dot on there is a galaxy, right? And it's pretty far from uniform, right? You see a lot of structure. You see voids, you see filaments, you see clusters and superclusters of galaxy, and you see this one feature which we call the Great Wall. This feature here looks like a string of galaxies, but we have other samples, so we know it's like a big sheet of galaxies. And so that's one of the surveys. The other survey is, it was mostly American done. The other survey is mostly European, mostly by England. But here we're doing a fly-through. And you'll notice as we go by you have not only the color information, but you have the kind of galaxy it is and other things that go with it. And so this is the kind of thing. It is very much harder to understand it when you're flying through it than when you go outside and look back and see the fan shape and see the overall structures. And so we're going to swing back around and look back, and you see you're just limited by the technology you have, that you're going to go and have a cone, and you're going to drag that cone across the sky, so you're going to get these fans on the sky. But you'll see the structure where you see this series of voids, that are in here, places where there are almost no galaxies, and other places where you have large clusters of galaxy. And it kind of looks foamy. That's the kind of a structure that you see. Okay, so right now we have a proposal in to go from that original survey, which I'm showing you is this little sort of purple area in here. That's the sort of purple spots in here that we're showing the fans of. The thing that's going on now is Sloan 3 BOSS, which is doing about 1 million per year, and now it's just finishing up its second year, and that's going out to this sort of red area. And then we're proposing to do Big BOSS to go out to this green area, and then at the end of each of these little strings is a quasar, and you want to measure the spectra of the quasar and see the intervening gas absorbing material, and therefore you can reconstruct a whole line of sight until you get into galaxies in terms of what's going on. So that's the kind of structure, and this is very similar to what you're describing about, you know, the bubble chamber taking data and taking more and more pictures per year. It's the how can you process more and more galaxies per year and put the information together. And how did we get there? Well, we had an extremely uniform universe at the beginning. Then we let gravity, you know, take its course over billions of years. And first you get little spots that form, and those little spots link up into kind of a spider web or a dirty cobweb kind of a structure. And so we'll recycle back as soon as we get to the present, go back, you can see spots appearing and then linking up and making this kind of a web structure. Now this is a simulation of an ideal kind of matter, which we call cold dark matter. That is matter that only interacts gravitationally, and you just let the tiny perturbations grow over time, and the place where it's overdense attracts material, the places underdense material flows out of. And so then you can do a full ups kind of a thing where you have not only the dark matter, but you have ordinary matter too. The ordinary matter is then come to form. So here's the end of the simulation. You see what the universe looks like, and we're going to zoom in. So 3 gigaparsecs is 3 billion light years. So as you zoom in, you see the voids. You see what look like a lot of filamentary structures. It looks like a lot of biological system. It's kind of a similar kind of stochastic nonlinear process going on that is tying things up. And of course, in this thing, they're zooming in on the place where a lot of filaments come together. That's where you get a supercluster of galaxies. So we don't live in the center of our own solar system. We don't live in the center of our galaxy. Our galaxy's in a tiny group. If we lived in a group like this, we would see galaxies everywhere we looked. We just live in a little, you know, a little village on the outskirts of a much bigger set of galaxies. So as you zoom in, I guess I'll let it zoom out. I'll skip over some of the other. So when you're in the middle of it, it's very, sorry, I should have turned Skype off. When you're in the middle of it, it's hard to see, but if you're a physicist and you can get the whole map, then things look a lot simpler. All right, so I'll skip the fly through, because that's really, so here's our concept. We can map out the history of the universe with simulations, and then we can try and map it out with our observations, see if it agrees. At the beginning of the universe, things are hot and very smooth, and we have, you know, the particle manufacturing going on, and then we have the primordial nucleosynthesis, then we have the first objects appearing, and then we have a fairly still uniform universe, although with spots in it, and then over time, this sharpens up and sharpens up until it gets to be quite crisp. I'll show you the same pattern without the labels. So you can see how smooth it is here, and then how structure begins to form, and then as you get closer and closer to the present, right, so the light has less travel time, the sharper and these features that you kind of see. Okay, so we're in an era in cosmology, like the same error in the, you know, this discovery of the Earth, of finding all the continents and mapping things out. So we started with COBE, where we made a high-resolution map, you know, with the galaxy and so forth removed. Here's a map of the Earth that corresponds. Here's a high-resolution map from WMAP, and eventually soon we'll have one from Planck. And here's the same equivalent high-resolution map of the Earth. And you'll notice a huge difference between these maps, right? The Earth has clear nonlinearities, which show up as these large-scale features, like the Mid-Atlantic Ridge, or this kind of ridge, or the edges of the continents. These things can only happen if nonlinear forces shape the surface of the Earth, whereas if you look at the universe, the things that shape space and time clearly had to be extremely linear. You don't see any features like any long, sharp edges. That you just don't see that. And you can do various analysis, but just your eye tells you that the forces that actually created space and time have to be extremely linear, and they have to be extremely simple kind of a thing. So we have the original data that came from this sort of thing came from these putting together various experiments. And I'm going to show you the galaxies, but I'm going to show you that not only have some of us cosmologists been busy, but the people who study stars have been busy, and they have mapped very precisely the location of roughly 1/2 billion stars. So we're going to see a few of them. 1/2 billion is quite a lot right there ahead of us. We haven't got 1/2 billion galaxies. But 1/2 billion isn't very many, because there's roughly 400 billion stars in our galaxy. So we have to do the French impressionists for the rest of the galaxy. Right? That's the problem. Okay, so we've got these measurements. Let me go to the final thing, because I want to go on to it. So we have the measurements now, which are not very many, where we've measured fairly precisely n tight. We got samplings further out, and then we have almost nothing. But we only have little wedges in here, but we have a pretty good map of the very beginning of time, and we're improving on that very quickly. And so we are making approaches to that. We still have to fill in lots of slices here in order to really compare with our model. And so I want to skip over the spacecraft and go back to the summary, because Bob has told me I have 2 minutes for 2 minutes. So the things I wanted to, I was going to tell some vignettes, but I wanted to show you pretty pictures more than that. So Luis Alvarez, I remember him being incredibly creative and inventive and really having ideas all the time. But he's not the only guy that has a lot of ideas, but his ideas are always, by the time they got to us, they were always pretty solid. And he was careful and strong about his science standards, and he really applied critical thinking. And the other thing he did is he taught me to take risks. Not that I required too much encouragement. You know, I got in my car and I drove out here and interviewed for jobs at Stack and at Berkeley. And then Louis is the one that hired me, so I'm not sure exactly what that means. But he left a tremendous legacy, both of people and his approach to things. And I wish Louis were still here for several reasons, but one of them is one of my grants requires me that I have 2 patents per year, and I don't have anywhere close to that. So I need Louis or somebody to give me a little help here. Okay, thank you.